Okay, everyone. It's my pleasure to introduce this week's colloquium speaker, Professor Boris Gaensicke. Boris is visiting us from the University of Warwick in the UK. And Boris initially started his career at the University of Göttingen in Germany, where he did his PhD, before he moved briefly to Southampton in the UK, and then on to Warwick, where he's been for about the past decade or so. So then during his time at Warwick, Boris has been awarded a prestigious multi-million ERC grant, which has enabled him to build up a substantial group around him looking at various aspects of post-main sequence objects. So in particular, he's looked at sort of compact binaries, accreting and detached white dwarfs, observational studies of white dwarf binary populations, and evolution of post-main sequence planetary systems. And Boris has already talked about some of those things over the course of the past couple of days here, but today he's going to focus on the post-main sequence planetary systems around white dwarfs. And he's led a number of groundbreaking observational studies of white dwarfs, looking at the pollutants that seem to be raining down into the white dwarf atmospheres, indicative of terrestrial type systems that are being broken up and are polluting the atmospheres of those white dwarfs. So with that, I'll turn the floor over to Boris.
So thank you very much for having me here. It's a privilege to talk about this topic here and today, and the reasons for here and today will become clear, I hope, in a minute or two. So I will talk about evolved planetary systems, and this is kind of the outline. I will give you a little bit of a background. I will talk about debris disks at white dwarfs, and I will talk about demographics of evolved planetary systems, and then conclude on what we can learn from these in terms of bulk abundances of exoplanets. So first, let's go into the background. Now, over the past 20 years, and it's only 20 years since the discovery of 51 Peg, we have learned that planets are totally normal. So stars like the Sun and a little bit less or a little bit more massive have planets. There's kind of nothing unusual about it. And so we can start to ask questions. What actually happens to these planetary systems once their stars evolve off the main sequence? And that then naturally brings us to the question, what happens to the solar system? What happens to the planets in the solar system when the Sun finishes its main sequence lifetime? And so the first thing we come across if we think about properties of planet hosting stars is that most of planets that we have found so far are orbiting F, G, K type stars, and there are a few around M dwarfs and a few around more massive stars, but the vast majority orbit stars in this range here. And they have all one thing in common. All of them will end their lives once they burn their central hydrogen core content. They will leave the main sequence, become red giants, and eventually evolve into white dwarfs. And so that means like pretty much every planet host today will end its life down here. And the question is, what happens to the planetary systems that it has had? So let's look at home. Let's look at the solar system. And I draw here to scale in solar radii the orbits of the terrestrial planets. So we are on number 3. We've got an asteroid belt. We have gas giants further out. And the Sun is currently halfway through its main sequence lifetime. So we're roughly here. And it's got another kind of 4.5 million years to go. So if we turn the clock forward about 5 billion years from now, the Sun will have exhausted or begin to exhaust its central hydrogen content. It will evolve off the main sequence and become a red giant. In that process, it will reach a size of roughly 1 astronomical unit. So the surface of the Sun will be more or less where we are here today. However, at the same time, the star loses mass, and the Sun will lose about half of its mass. And if I go back and forth between these two slides so that the scale here remains the same, you notice one thing. Well, you notice two things. A, the Sun becomes a red giant and evaporates everything that is within an astronomical unit. But because of the mass loss, every body that orbits, planetary body that orbits the Sun moves out. And so if we then turn the clock forward another little bit, kind of 7 billion years from now or 8 billion years, we will be left with a white dwarf and remnants of a planetary system. So quite early on, people have looked at dynamical studies of the solar system, basically integrated forwards the orbits of the planetary systems. So Duncan and Lissauer did that. And they concluded that the orbits of the remaining planets in the solar system will remain stable for billions of years. And so we are quite confident that that's the configuration we will look at in several billion years from now, that we will have a white dwarf, asteroids, probably a terrestrial planet, and gas giants around it. And so then we go and look at the known population of exoplanets, and that's a plot that is courtesy of Dimitri Veras. He put that together. So what I show here is the minimum mass in Jupiter masses. Quite a few of the stars up here are from radial velocity, so we only have minimum masses, and the semi-major axes of the planets. And I divide them broadly into two categories. The ones on the left will be engulfed once their host stars become red giants. And the ones on the right-hand side here, they will move out and they will survive the end of the life of their host stars. And so you see that there's a large number of planets that we already know today that will survive post-main sequence evolution. The solar system planets are the blue diamonds. And so you see that there are still large selection effects among the population of exoplanets. And it's quite sure that there are more planets down here and down here which we haven't found, and many of the ones that are over here will also survive the evolution of their host stars. And so the conclusion is that we can quite safely expect that many planetary systems will survive the main sequence evolution, and therefore there's no reason not to assume that many of the current day white dwarfs also have remnants of planetary systems around them. Now just a few key facts about white dwarfs, because I assume that some of you are not super familiar with the key properties of white dwarfs, and there are very few things that you need to learn for the next kind of half an hour. First thing is the size and the mass. So a typical white dwarf is roughly Earth-sized and has a mass of about half, 0.6, 0.65 solar masses. And so that has a very immediate consequence, namely that the surface gravity of the white dwarf is about 100,000 times that on the Earth. So you can imagine you have had your Christmas dinner and you step on a scale on a white dwarf and you have a bad surprise. It has a second consequence. It leads to the fact that in a white dwarf, chemical elements are stratified by weight. And so this is a slightly busy plot, and actually you would need to turn your head 90 degrees to really appreciate it. So what I show here is a cross-section through a white dwarf on a logarithmic mass scale. And this is the element fraction of the main constituents of the white dwarf. And so just to explain what it really means, the carbon and oxygen core, which was produced by hydrogen burning into helium, then helium into carbon and oxygen, makes up about 99% of the white dwarf mass. So 99% of the white dwarf mass are over here, and you see that oxygen is concentrated towards the core, and carbon, which is a bit lighter, floats up and sits largely on top of the oxygen. And so then if you move further out, you have some residual helium, which is floating on top of the carbon and oxygen core. And in most cases, you have hydrogen, which then floats on top of the helium layer. Now, if you ask yourself, what can we observe spectroscopically? Spectroscopically, on that scale, we are roughly out here at 10 to the minus 14. So that's what we see. If we observe from over here towards, observe a white dwarf, we look in this direction, and our line of sight stops here. And that means that the very simple assumption is that all white dwarfs should have pure hydrogen atmospheres, or in a rare number of cases, they may have pure helium atmospheres if a late shell flash removes that outer layer of hydrogen. So then you end up with a pure helium atmosphere. But you wouldn't expect to see anything else but hydrogen or helium. Now, as you know, there's always an exception to the rule, and that was actually a quite early exception here. You see here a modern spectrum of the third white dwarf that was discovered, and it's very nearby, it's at 4.4 parsec, was discovered by van Manen in 1917. He took a spectrum of it, photographic plate at that time, and he noticed the calcium H and K lines. And so he thought that it is an F star. Very shortly later, they obtained a parallax and realized that the star is very nearby, and so he concluded it is therefore by far the faintest F-type star known at the present time. It took them a little bit longer to realize that it wasn't an F star, but that it's actually a white dwarf with a solar-sized radius, and a very unusual spectrum with these lines. So the modern spectrum shows that there's not only calcium, but we have iron and magnesium, and these elements shouldn't be there because of the chemical stratification. And so here's a little excerpt from a paper by Alcock and Ilarianov from 1980. So it's good to be here and see that people have worked on that a long time ago. And they concluded gravitational sedimentation of heavy species is a rapid, efficient process in all white dwarfs, regardless of the depth of the convection zone. So you really shouldn't see metals. And that means that if we do see metals, they must come from external pollution. There must be somebody sprinkling metals on the white dwarf, here and now or quite recently. And so that is where the story pretty much stopped in the 80s or so, 1980s. And the general assumption back then was that these stars accrete from the interstellar medium, because we didn't know anything else. We didn't know that there's other material around that they could capture. The problem with interstellar medium is that there isn't enough of it, and we have some of these white dwarfs with helium atmospheres. Now the interstellar medium is composed mainly of hydrogen, and if you accrete interstellar medium, you would very rapidly actually build up a hydrogen layer that you could detect. The detection of, for example, this particular star that has a helium atmosphere, it has metals, but it has no detectable amount of hydrogen, so it would need to have some kind of complicated screening process that accretes metals from the interstellar medium, but not the hydrogen. So that was a little bit kind of a problem to explain the existence of this star. So stepping into the next chapter, planetary debris disk at white dwarfs. In 1987, Zuckerman et al., they were searching for brown dwarf companions to white dwarfs. They found an infrared access to one white dwarf, G29-38 is its telephone number. And you see in this diagram here a modern spectrum of it. So that's an optical spectrum over here in the optical wavelength range. And that's the infrared wavelength range observed by Spitzer. And this line here is the white dwarf spectrum. You see the hydrogen absorption lines from the white dwarf photosphere. And what you see is a whopping infrared excess. Now, this is one of the few stars that was sufficiently bright to be observed with the Spitzer IRS spectrograph. And so there's a spectrum. You see that emission bump here. And people who understand about mineralogy have looked at that, and they say that it's silicates. And not only silicates, it's olivine. And I come back to that in a second. So olivine is kind of this green type of sand. Okay? So observations show that there are white dwarfs that have metals in their atmospheres and that have dust, sand around them. And that's not what you expect for a white dwarf, because it's in the center where there was once a star, red giant, kind of one astronomical size big, that would have evaporated everything inside there. So doing statistics shows that a small number, few percent of white dwarfs have dust disks around them. So that's not a huge number, not a huge fraction, but it's actually, there are many, many white dwarfs, so it's actually, in terms of absolute numbers, quite a large sample by now. Now, a few years later, James Grahame looked at the evidence, because people were still unsure whether that infrared excess back then was a brown dwarf or something else, and he came up with this visionary statement. Now you have to read this and you have to look at the date. This is 1990. This is 5 years before the discovery of exoplanets. And here there's someone who says, well, there's a white dwarf and it has dust around, it has an infrared excess. Maybe it's dust. Where does the dust come from? And he says, well, particles couldn't be there because that's where the red giant was before, and the putative dust cloud must be the debris of some relatively recent catastrophic event, such as the near collision between an asteroid or comet and the white dwarf. And so that was really the foundation of what we talk about today, disruption of planetesimals around white dwarfs. So you have an asteroid that is perturbed, gets too close to the white dwarf, gets tidally disrupted, circularizes from the disk of dust that then rains down and explains the metals. And you may say, well, how often does that happen? In the solar system, it actually happens quite often. This is a movie from Soho, couple of days. Let's watch that one time. So we see two comets coming into the sun. The white circle is the radius of the sun. And that's the tidal disruption radius around the white dwarf. So you need to get an asteroid within here and it will tidally disrupt. So we see that these things happen in the solar system very frequently, and therefore it's not kind of totally total speculation that this might happen around other stars. So the next step forwards in the kind of study of these disks was that we discovered this star in 2006. By now, I hope I have trained you enough that you could look at it and tell me what it is. This is a textbook white dwarf, but with very strong Balmer lines, hydrogen absorption lines here. But there is something odd in the red end. So when I saw that spectrum, I thought initially that's an instrumental artifact, and I put it aside. And then I took it back and said, well, that's actually funny because this coincides with the calcium-2 triplet in the I band. And then if you look very closely, these emission lines are actually double peaked, and so they don't really look like any artifact. And then you look close and you see there are other emission lines over there from iron. And if you squint, you can see there's a little absorption line over here from magnesium. So we have a white dwarf, which looks almost like a textbook white dwarf, but it has emission lines that white dwarfs shouldn't have, and it has an absorption line. Well, that wasn't totally unusual because we knew white dwarfs have metal absorption. Now, these emission lines, they're really exciting. So first thing is, these things are extremely rare. We found one, we got excited, and we started to look for more of them, and we found a few more, but they're very rare. It's about 1 in 1,000 that looks like that. Now, having these emission lines is very, very exciting because we can tell that they come from a disk. You remember I said there's dust around white dwarfs? But an infrared excess doesn't really allow you to tell anything about the geometry. You assume that's a disk because that's the natural thing, but it could be a cloud. If you see a double-peaked line profile, you know that you have a flat Keplerian rotating disk of dust. You know that the material is in a plane and rotates around the white dwarf. But it's better than that because the line profile tells you something about the intensity and velocity distribution in the disk. So that goes back to work by Horn and Marsh. And you have to imagine if I'm an observer over here and I look at an accretion disk, I've got parts of it that move towards me, I've got parts of it that move away of me, so I get a combined blue-shifted, red-shifted profile. And if I have a symmetric intensity distribution on a circular disk, I get a symmetric double-peaked line profile. That's just the projection of the velocities of the disk along the line of sight. So we got that first observation, and if you look very closely, you can see that the lines aren't quite symmetric. So the red peak here is stronger than the blue peak. And so back then, when we made that discovery, we thought that the disk is slightly eccentric, and we thought that's interesting. Let's see what happens with time. And we kept on observing this star for 12 years, and here you see a time sequence starting in 2003 with the Sloan spectrum. Going down, you see that the line profiles evolve to something that looks like a textbook symmetric double-peaked line profile. And then going down in time, the blue peak starts to become more and more dominant, very sharply peaked. And then around here in 2010, the red wing moves out to higher velocities, which means it moves deeper into the potential of the white dwarfs to higher Keplerian velocities. It develops a very sharp edge. It turns out that we can explain that whole sequence with a fixed intensity pattern on the disk that precesses with a precession period of the order 25 years. So we believe we are halfway through a precession cycle of an intensity pattern on the disk. And we can apply a method which is called Doppler tomography to convert these line profiles into an image. And so we have now the first image of a debris disk around the white dwarf. Now it's an image in velocity space. So you have here velocity around the white dwarf, and it's therefore inverted. You have the low velocities that you have in the outer edge of the disk inside. This is 2 solar radii. And the inner edge of the disk, where you have the highest velocities, is outside. That's 0.2 solar radii. And if you look very hard, you see something that looks like a spiral pattern that starts here and then moves out. Okay? So we think we see a spiral pattern of gas on top of the dust disk that precesses with time, which is remarkable because the orbital time scale is hours. Okay. What does it all mean? We think what we see here is a young debris disk that hasn't circularized, that is slightly elliptical, and general relativity would lead to precession on a timescale of decades. Now this is speculation. It may be true, it may not be true. But we have debris rings in our solar system. We look at the rings of Saturn, and they are now nice and circular, but they weren't initially. They must have formed in a fairly messy dynamically violent process and then circularized with time. So what we think is that we see something like that in its early phase. And to put the two kind of on scale, this is what it looks like. This is Saturn in scale to the spiral pattern that we see in the emission lines. You could fit Saturn into the inner gap here. Why do we have an inner gap? We have dust outside, gas on top, and then we have an inner gap. The white dwarf is fairly hot, 20,000 degrees, so it sublimates the dust at about 0.4, 0.5 solar radii. And then we have a gap where you have gas flowing onto the white dwarf. Now this is where the today comes in. Why is it so great to talk about this today? Because yesterday there was a paper in Nature by Andrew van der Boek where they detected for the first time debris directly around a white dwarf. So they detect in K2 light curves transits every 4.5 hours. So they see material that blocks the light, and the shape of the transit changes with time. And they actually don't detect only one debris, one disintegrating planetesimal, but possibly up to 6. And a spectrum of that white dwarf shows surely that it has metals, as accreting debris, and it has an infrared excess, so there is dust around it. And so that's fantastic because it's a real unique confirmation that this whole scenario, which I explained you, is true, and it will be exciting to see what happens to this system over the next years. Good, so coming back to the idea of you disrupt an asteroid, we've done a few simulations of that. So you start out with an asteroid fairly far out, and you throw it towards the white dwarf. It is on an extremely highly eccentric orbit, eccentricity 0.99 something. It will disrupt, and in the absence of other forces, if you only assume gravity, what happens is it gets disrupted. The cross is where the white dwarf is, and I show here several orbits. It breaks up into particles and forms eventually, after many orbits, just an elliptical ring of debris. And so we are now in the process to add more physics, radiation, and collision to work out on what time scale this ring will be drawn inwards to the white dwarf and form a disk. But you can imagine that it can take quite a long time. And at the ITC luncheon, we saw movies similar to that. So what we think what you think happens, or what must happen around the white dwarf, is the same thing as the tidal disruption of stars around black holes. You have a star coming in, or in our case an asteroid. The white dwarf or the black hole is in the center. You disrupt it, material flings out, comes back, impacts with itself, and forms a very messy, complicated structure that with time will then circularize into something nice like Saturn's rings. Okay, so that's how we think we can explain all the observational evidence, metals in the photospheres, dust, gas emission lines, and now the detection of transits. And so we know that there are remnants of planetary systems around white dwarfs. Next step is what else can we do with them? What can we learn from there? So next step, the next thing I want to talk about, is demographics of these evolved planetary systems. So the situation that I described looked like this. You have a debris disk that is shown here. Currently we have no real idea about the size distribution. We know that there's micrometer-sized dust. That's what we see in these Spitz observations. And until yesterday, we didn't know anything else. Now we know that there are bigger chunks going around, and we know there's gas, and so that stuff then rains onto the white dwarf, into the atmosphere, and gets dissolved. So what is in here, rocks, maybe ice, will be dissolved into atoms, and they will diffuse down with time. But before they diffuse down, we can take a spectrum of it, we detect the elements. And so, in simple words, the detection of metals implies that we see a white dwarf which has remnants of a planetary system. And that makes the process very simple. Rather than looking for infrared excesses or transiting events, we just need to detect metals. So metals are a tracer of planetary systems around white dwarfs. And so how you go about that is shown here. You probe for calcium H and K absorption. And you can do that from the ground. So you just need high-resolution spectrographs. The problem with white dwarfs is they're Earth-sized. They're still quite hot, but they're Earth-sized, and that means they're very faint. So that means you need big telescopes. And most of the work that is shown on this graph here has been done with the VLT and Keck high-res. And what I show is the white dwarf effective temperature down here. That's the typical range where you find white dwarfs. and the cooling age up here. So the two scales are opposite. White dwarfs cool with time. Here we look at stars that have ended their main sequence lifetime 20 million years ago, and they have temperatures of around 25,000 degrees. And they cool down to about 5 billion years, half the age of the Milky Way, and they reach a temperature of 5,000 degrees. So at low temperatures, calcium H and K is a very strong signature of metals, and we can detect, measure, count the fractions of stars. If we move along that sequence to hotter stars, younger cooling ages, calcium-2 becomes calcium-3, the calcium H and K lines disappear, so we need to find other transitions, and the optical is not good anymore, but we need to, okay, I forgot about one slide in the middle, so let's first look what happens over here. So the calcium H and K is a good tracer, and we found now some really extreme stars. You look at this one, and let's say 5, 6 years ago, you would have shown me that spectrum, I couldn't have told you what it is. This is an extremely cool and extremely metal-polluted white dwarf. Temperature of around 5,000 degrees, cooling age of around 5 gigayears. And what you see here, this depression, this is calcium H and K. So the calcium H and K line is about 1,000 angstrom wide. And that's because the star is so cool. It has pressure and pressure broadening of these lines, and has a very large amount of calcium in the convection zone. And that's exciting because this star is eating a planetary system that has finished its main sequence lifetime before the solar system was formed. So we look at debris of planets that formed way before the sun itself. And that means we can, in principle, look back in time into the abundances of planets that formed early on in the Milky Way. And we can, in principle, look at statistics of rocky planet formation. There's a lot of work that needs to be done. In particular, like theory becomes really difficult. These stars, they're cool. They have almost liquid atmospheres, so theory is difficult. It's warm, dense matter. You have problems with the equation of state, line broadening, feedback of the metals into the atmosphere structure, and so on. And that's all work in progress. Good. Coming back to this diagram. If we want to work our way upwards to higher temperatures and younger ages, we need a different tracer for the metals. And it turns out that the best one is silicon in the ultraviolet. So you see here an HST spectrum at 1260 angstrom, and you see these very strong silicon resonance lines. And so that means it's very easy. You just need to observe stars in the ultraviolet. Very easy in principle, because there's only one instrument that can do that. That's the Hubble Space Telescope. It has a fantastic spectrograph, the Cosmic Origin Spectrograph. But you compete with a lot of people doing all kinds of exciting stuff, exoplanet atmospheres, cosmology, and so on. And we were quite lucky that we managed to observe in cycle 18 and 19, 85 hydrogen atmosphere white dwarfs with temperatures of 20 to 200 million years, cooling ages. And I show you one up here, which is a textbook white dwarf. So what you see here, that large depression, that's Lyman alpha. That's the transition from the ground state to the first excited state of hydrogen. And so it's a textbook white dwarf because it doesn't have any metal lines. I expect that some of you rebels because you look and you say, what's there? There are metal lines, but there are actually metal lines, and I can tell you what it is. That's silicon, oxygen, and carbon. These are lines in the interstellar medium. So COS is so sensitive, has such a good resolution, that even in a spectrum, this was maybe a 1,000-second spectrum of a white dwarf at 15th magnitude, we see the interstellar absorption lines along the line of sight. And here's just sorted by the amount of metal pollution, the stars that we found in this survey. So it turns out that some of these stars have amounts of metals in their atmospheres, like this one down here, that you can't actually define a continuum anymore. It's lines everywhere. And all these metals are accreting onto the star right now. The reason for that is that in this sample, these are hydrogen atmospheres, and these stars have extremely short diffusion timescales, days, maybe weeks. And that means if I could turn off accretion within a month or two, this star would look like that, because the metals would sink out of the atmosphere. And so that means these stars are accreting right here and right now. A few of them have infrared excess detected, some of them not. But we can then move on and say, well, what does it actually mean? So focus just on the middle panel. This is a fraction, and we look at the fraction of all white dwarfs observed either from the ground or in the ultraviolet, and we see that we have metal pollution in roughly 50% of all stars. So we conclude that the fraction of white dwarfs that have evolved planetary systems is somewhere between 1/4 and 50%, and that's totally comparable to the frequency of planets around solar-like stars. You may say, well, that's not terribly surprising because we knew that planets are everywhere, and we know that planet house evolved into white dwarfs, and we think that something should survive, therefore no surprise here. But would you have asked me 10 years ago, I wouldn't have predicted that. There's still a few gaps where we don't have terribly good data, so at kind of intermediate cooling ages of a few 100 million years and at very young cooling ages. And so we're in the process of filling these in. And here's just a recent spectrum which shows, yes, you get hotter white dwarfs cooling age of about probably 10 million years, and it has metals in the atmosphere. And so we'll see how the trend looks to the kind of youngest ages. Okay, so now we see that we basically have shown that planetary systems are almost omnipresent also in the final stage around white dwarfs. And so I will spend the final part of the talk on bulk abundances. Bulk abundances are really important. People get extremely excited about transit spectroscopy of exoplanets, and it is very exciting, but it only gives you abundances for the, as it says, the atmosphere. Now the atmosphere is a minute part of the star, and especially for rocky planets, if we could do transit spectroscopy, which is still very challenging, you think about the Earth and Venus. They have totally different atmospheres. You could do transit spectroscopy of the solar system, potentially, if you were an alien. And you would learn that there are two planets that have very different atmospheres, but their bulk compositions are probably very similar. And so you learn about the atmospheres. If you want to improve models about planet formation, you need to know the bulk abundances. And now you may ask yourself, well, how do we actually know the bulk abundance of Earth? We can take rocks, we can measure their abundances, we can drill a little bit, but we don't know, we can't measure what the core of the Earth is made out of because we can't drill down there. So we know the bulk density of the Earth, and we have models of planet formation. And the really important ingredient is that we know the building blocks from which the Earth was made. So we know the original material that was put together to make planets. And we know that from rocks that fell from the sky. So we look at meteorite abundances, and we find very different types of meteorites, and that tells us about the composition of planetary bodies in the solar system. Now in these white dwarfs, we do exactly the same. We have rocks, and I will show in a minute that these are rocks, that get disrupted, they fall onto the white dwarf, and we detect them. And so applying knowledge of physics to the data that we get, we can then infer backwards the abundances of the material that was accreted. And so it's precisely the same mechanism that we use on Earth to learn about the abundances of the solar system, of planetary bodies in the solar system. Just to illustrate you how rich the data is, I blow up in this panel here a little snippet from the spectrum down here. And you have to probably squint a bit to see what I have plotted up there. So we have in black the data, and in red the model. And so we see absorption from silicon, iron, phosphorus, sulfur, chromium. And I think that's it in this panel here. But we detect in some of these stars 12, 15 different chemical elements. And so that means we can measure the abundance of exoasteroids, exoplanetesimals, with pretty high precision and for a large range of elements. We analyze these data with an updated atmosphere code, which includes diffusion calculations, radiative levitation, so you need to take into account that you've got radiation pressure lifting some elements up or supporting some elements stronger than others, updated atomic physics, and work out the abundances in the atmosphere and therefore the abundances in the accreted material. And once we have these abundances, we can then put them into the context of what we know from the solar system. The planetary science people in the solar system, they like to look at abundance ratios, and they like to normalize to silicon. The reason for that is that silicon is the major rock-forming element. And so lucky, because silicon is the element that we are most sensitive to, we can do the same thing. The first thing we notice is that 4 elements, oxygen, magnesium, silicon, and iron, are pretty much always the major constituents of the debris that rains down on the white dwarfs. And it turns out that the Earth is made up to 90+% of oxygen, magnesium, silicon, and iron. And then if we look in a little bit more detail, we find that most of the stars that we have looked at are carbon depleted. So that's illustrated in this plot down here. This is a log scale. And on this axis, I plot the carbon to silicon ratio. The little dots are meteorites. So these are abundance measurements for meteorites in different colors. You can see them a little bit better here. Different colors represent different meteorite families belonging to different parent bodies from the solar system, in the solar system. The sun is over here. So carbon to silicon for solar abundance is over here. Chondritic meteorites are over here. We think that these are the kind of primitive leftovers from the planetary protoplanetary disk in the solar system that reflect the abundances of primitive asteroids. And the Earth sits down here. So the Earth has roughly a factor 1,000 less carbon relative to silicon than the sun. So the Earth is carbon depleted. And the big colored dots with error bars are the white dwarfs that we have observed. And so they are, within the error bars, very similar to the bulk abundance of Earth. And so therefore we think this is rocky material similar to the inner solar system. The second thing, and that was probably the best test, and that really showed that this is not complete fantasy what we're doing. You look at elements like calcium and aluminium, they're called refractory lithophiles. And so if you think about planet formation or things that go on in a planetary system, you form small bodies, meteorites. They will collide. They will be heated up. Some of them will melt. You will have gas. You will condense again. If you form larger bodies, they will differentiate. So you will have iron, nickel sinking to the core. And you can undergo a lot of very complicated processes that will alter the compositions of your planetary bodies. However, some elements like calcium, aluminium, and titanium belongs to that. They have very similar properties. So whatever you do to your planetary bodies, the ratio or the relative abundances of calcium and aluminium stays constant. And so this is shown in this diagram here. Remember, the little dots are meteorites. This is the ratio of aluminium to silicon on a log scale, factor 100, and calcium to silicon, again a factor of 100. And so in the solar system, all the meteorites, they fall on a line because calcium to aluminium remains constant no matter what has happened to these planetary bodies. And the few white dwarfs where we have data so far, they follow this trend within the error bars. And so that means that this actually makes sense. This is not pure randomness, and our analysis and interpretation is valid. Then we can look at the amount of iron, and that's shown here. So I show iron over silicon, and there are a few stars which have very large amounts of iron. And in some of them, we also see overabundances of sulfur and chromium, and we think that those elements are also drawn into the cores in the process of differentiation. And so we think we see things comparable to iron meteorites or stony iron meteorites in the solar system. I show on this plot here, I show a photo of a stony iron meteorite or a mesosiderite. It has a name, Vaca Muerta, was found in the desert in Argentina. And the iron and nickel abundances in this meteorite are very high. So these are in a database of a few thousand meteorite samples. It's the highest nickel and iron to silicon ratio. You can be higher. You can have almost pure iron meteorites, and there's no silicon that you can measure, and then you're kind of off the scale. This is the highest nickel and iron to silicon ratios that are measured. And the parent body is thought to have been a kind of few 100-meter sized asteroid that differentiated and then at some point in the early phase of the solar system broke up, and fragments of it kind of now fall down. And so we have one white dwarf which has kind of almost the same amount of iron and nickel, and therefore we think what we see there is accretion of a planetesimal that has undergone differentiation, broke up, and is now accreting onto the white dwarf. I told you about rocks and differentiation, And I show you here rocks. Now, what are rocks? Rocks are metal oxides. In exoplanets, there is now more than finding exoplanets. It's a lot about life and habitability, and that's always linked to water. So the next question is, can we actually tell something about water? Now, water and rocks have one thing in common, and that's oxygen. When I talk about rocks, or rocky material, or terrestrial planets, what I mean is metal oxides. It turns out that almost any mineral, you can break it up into these individual compounds, so something like magnesium oxide or silicon dioxide. That means if I have rocks and I look at their abundances and I can measure how much I have of each of the individual metals, I know how much oxygen there should be if it was just rocks. Because I know, for instance, that every silicon atom brings in 2 oxygen atoms, and every magnesium brings in 1 oxygen, and so on. So we have a prediction for how much oxygen we would expect to see if we accreted some kind of mixture of rocks. And so if we look very closely at a few white dwarfs, and again, COS was instrumental here because it covers 2 oxygen lines. Oxygen is very difficult to measure. Kind of from the ground, there's basically just one transition at 770 nanometer. In the UV, we have 2 additional ones, so we have 3 lines of oxygen. Hope that the measurement is robust. So if we do that, we find a few stars where we see an oxygen excess. So we have more oxygen than we would expect from the metals. And we detect all the relevant metals in the atmosphere. And then you sit down and start to think, where does the extra oxygen come from? And you have basically 2 or 3 options. You have carbon monoxide, carbon dioxide, and water. Now, I just told you that these stars have very little or no detected carbon. That rules out carbon monoxide and carbon dioxide. And that means you're left with water. And water brings in kind of H2O, brings in the oxygen. And we can, from the oxygen excess, we can estimate the water fraction. And from the kind of depth of the convection zone and the total amount of metals, we can estimate the mass of the parent body that was disrupted. And we come up with these numbers that we have a parent mass in this range here, 10 to the 21 to 10 to the 23 grams. And we have a water fraction of about 25%. If we look at these numbers and we look back into the solar system, we see that this is not kind of totally unusual. There is a body, solar system body, the largest asteroid, Ceres, which pretty much fits that description. Here's an HST image of Ceres. And this is how planetary scientists think Ceres looks like, that you have a rocky core, and you have a thin crust on the outside, and then you have a mantle of water ice beneath it. And Dawn is a space mission which is in orbit around Ceres, and hopefully we'll get more results soon. But if you Google, you find that the industry was already there. So they bottled the water from Ceres, and you can buy it in the supermarket. So that came to a surprise as me. And so, so what we think is that we see in that particular white dwarf, we see accretion of a Ceres-like body, which was a mixture of rocks and water ice, or hydrated minerals. So we can't say for sure if it was water ice or hydrated minerals, but it had large water content. And that's important in at least one context, in the context of where do we get our water from. So the Earth was probably formed dry. People argue about that a little bit. But a large number of people think that the Earth formed dry and water has been carried to Earth after the formation. And you may ask, how do you get water on Earth? You need to have water-rich bodies. And there are 2 alternatives. You can have comets. Comets are very high in water content, but they have typically low masses. So you need a lot of comets to hit the Earth and deposit the water. An alternative is that you have large water-rich asteroids. So if we look at numbers, the mass of the Earth is 6 times 10 to the 27 grams, but it's extremely dry. It has kind of 0.02% of water. And so the total mass of water on Earth is of the order 10 to the 24 gram. Now if you look at Ceres, which is shown here to scale, it has a mass of 10 to the 24 gram, but it has a mass fraction of about 25% water, so it has 2 times 10 to the 23 gram of water. And so that means if you just look at the simple numbers, you would only need 5 of these things to bring the water to Earth. Now, I don't claim that that is what happened. It's a simple thing to look at the numbers and say, this is something you could think about. And I have the moon on here because we don't know how much water is on the moon, but people get very excited about that, so I thought I'd just show it. Good. We can investigate some more exotic things. If you are into exoplanets and follow the literature, there has been a huge discussion about carbon planets. The reason is the following. Carbon and oxygen really like each other. So most carbon and most oxygen in a cold environment will bind and form carbon monoxide, carbon dioxide. Now, in our solar system, we have more oxygen, and that means most of the carbon is bound, and you have excess oxygen, which then forms with metals, rocks, and water, as I just showed. Imagine the opposite. Imagine a solar system where you have more carbon than oxygen. Then all the oxygen is tied up in carbon monoxide, and you have no oxygen left to form rocks or water. But you form carbides, so you form silicon carbides, and you form carbon planets with possibly diamond cores or so. And so there has been a lot of speculation about carbon planets, and some studies of atmospheres show a high carbon to oxygen ratio. And there were some speculations about carbon-rich interiors in super-Earths. So we can actually measure the carbon to oxygen ratio, and that's a paper that is submitted by a student of mine, where we look at the carbon to oxygen ratio of, if I remember correctly, 16 white dwarfs, where we have either a measurement for carbon and oxygen, or we have detected oxygen and we have a limit for carbon. And we can then put them into this diagram where we have the effective temperature here. And we have log of the CO ratio. And you would expect things that sit above that line, or I should be a bit more precise, planetary systems that formed above that line would be carbon dominated. However, if you form above that line, just as the Earth is carbon depleted, a carbon planet would be severely oxygen depleted. So a true carbon planet would kind of be probably off the scale here, off the diagram at least. And so we have here the bulk Earth, and we have chondrites, which, if you remember, I mentioned are the kind of primitive building blocks, the kind of first generation asteroids that formed in the solar system. And we have Comet Halley, and we have the Sun. And it's quite interesting because it looks like there's a bimodal distribution. So you have CO ratios that are Earth-like or even below, and you have chondrite-like material. But we found no evidence among this sample of 16 stars for large carbon to oxygen ratios, so we can put a limit on the frequency of these stars, which I forgot the exact number. I think it depends on the significance, and I think it was 16%. So we don't rule them out, but they are not frequent. Good. So looking into the future, like coming to the end of the talk, and looking into the future, where do we go from here? The thing that everybody asks, like, where are the planets? We haven't found a planet around the white dwarf yet. We have found, as of yesterday, planetesimals, but no proper planet. The reason is it's hard. If you think about methods to find exoplanets, you have radio velocity and transits. Radio velocities are basically impossible because white dwarfs are small, they are faint, and they don't have a lot of lines. So you will, I don't want to say never, but not in the near future, be able to measure white dwarf radio velocities down to meters per second or tens of meters per second. And I come back to transits. What I think is probably the first method is astrometry. Because astrometry is actually more sensitive to planets that are further out, because the planet and the star go around their center of mass, and if they're further apart, the center of mass moves further away from the star, so your astrometric signal becomes larger. Gaia will observe hundreds of thousands of white dwarfs, 200,000 to about 500,000, and the sensitivity should be good enough to detect an astrometric wobble, so a shift of a white dwarf being pulled by a planet. And we should know that in a couple of years from now. Now, preparing for that, because by that time HST will be history and there will be no UV instrument left, we decided that it's probably a good idea to get UV spectra of all nearby white dwarfs within 13 parsec, because if we find a planet around one of them in 5 years, we would like to say what is actually the composition of the debris. and we wouldn't have an instrument. So we just said preventive, take spectra of all the white dwarfs within 13 parsec. Okay, so and Gaia will discover 200,000 white dwarfs, which feeds then into the next things. What comes next? There are a very large number of multi-object spectrographs, and I only list 3. There are many more that are kind of in the pipeline. So we will have, in 10 years from now, massive abilities to spectroscopically follow up interesting objects. Now, interesting objects are usually quasars and high redshift galaxies or intermediate redshift galaxies, but we only need a tiny fraction of the fibers of these instruments to observe all white dwarfs that Gaia discovers. Yes, it just takes like 1–2% of the fiber hours to get spectra of all white dwarfs with kind of these typical parameters, and from this we can measure temperatures, surface gravities, masses, radii, cooling ages. We can detect metals, and we will identify through metals thousands, maybe 10,000s of evolved planetary systems, and then do proper statistics of abundances and incidence as a function of cooling age. And one thing that I didn't mention is, in principle, from the white dwarf mass, we can infer the progenitor mass. So we can look at the incidence of planets as a function of main sequence progenitor mass. We haven't done that yet because we don't have enough data. Then we move forward to James Webb. Now, James Webb will be fantastic because I showed you this one IRS Spitzer spectrum of dust where we see silicate, like kind of green sand. We can do that with Spitzer, but so much better. And now we can combine the two things. We will have a handful, and not a huge number, maybe a few 10 white dwarfs, where we have ultraviolet spectra of the material in the atmosphere of the white dwarf dissolved, so in ions. So we can measure the individual atomic abundances of the material falling into the white dwarf. And for the same stars, we can measure the mineralogy of the dust around it with James Webb. And then people who work on minerals can take this as an input because they know the abundances of your dust, and they can work out what kind of minerals can I actually build from the stuff that I have. This is a plot from Bill Reach for G29-38, where he made a very complicated composite model for the IRS spectrum. And he included things that we know now, carbonates. We don't have carbon in that star. So we can go back and say, well, now we know abundances for that one star, and we need to reproduce that spectrum without carbon. So things like that. Then there are large infrared surveys, Euclid and WFIRST, and they have the potential to detect hundreds, maybe thousands of dusty debris disks through infrared access. And if the timeline works out between these survey missions and James Webb, you can follow those up with James Webb. NSST comes along, and it will observe like millions of stars, not millions of white dwarfs with 1,000 epochs, and you can then search for transits. So I talked about radial velocities. Why are transits not a good idea yet? The reason is that I showed you this diagram. So planets should be far out. And that means if they transit the star, they do it only fairly infrequently, every couple of years. Plus the probability that you're aligned with a planet is extremely low. Now, it's not clear that planets will stay there, because if you have multi-planet systems, you can have dynamical interactions, and you can actually have planets scattering each other onto eccentric orbits, which will bring planets closer in. And so that's from a paper that we published earlier this year, where you have the cooling age and the pericenter of planets, and we start with a 10-planet system that evolves off the main sequence. They move out, as I described you. And then they start to interact, and they scatter each other, and some of them get ejected, and some get scattered very close to the white dwarf, where you could, in principle, detect them easily by a transit. The orbital periods would still be long, but it increases the geometric transit probability. And then finally, looking kind of, this is like more the realm of science fiction. That's the next ultraviolet mission, which goes, I have it here as at last, it's now probably HDST, the High Definition Space Telescope, a 8-meter mirror with the UV spectra and optical spectra and everything. And so you could then do these abundance studies for several hundred stars, and you could populate a diagram like this, where we have now kind of maybe a dozen stars with hundreds of points, and you could do proper statistics about the bulk abundances of planetary systems. Okay, so that's where the future is. And just to wind down, I just summarize very briefly. Planetary systems are very frequent. But host stars evolve off the main sequence eventually. They destroy the innermost planets. Mass loss will widen the orbits, which can lead to dynamical instability. So you can have, in principle, planet collisions, or Matt Payne is working on a paper on moons. You can strip off moons and eject them, and something may happen to the moon. So a lot of things can happen. But eventually you will end up with white dwarfs that have remnants of planetary systems, and in a fairly large number of these systems, asteroids get scattered close enough to the white dwarf to be tightly disrupted, form an accretion disk, accrete onto the white dwarf, where we can then study the bulk abundances. And I stop here.
Thank you very much, Boris. Does anyone have any questions to start with?
So in the white dwarfs with very short settling timescales, do you have multi-epoch observations? Does the pollution remain the same the whole time?
Yes, that's the typical question we get. Yes, we have the system which I showed where we have 12 years of data. We also have data for the absorption lines. And within a few sigma, they don't change. And we don't really know why. So it suggests that the accretion is very steady, very homogeneous, which is not quite what you expect for the messy things that we see in the lines or in the disintegrating planetesimal.
So you mentioned the likelihood of having these asteroids and rocks, small rocks, but why wouldn't you imagine also the planetary nebula perhaps leading to a new generation of planets that could be actually closer to the white dwarf? In other words, these were not the old ones, but you can form planets close to the white dwarf, all the way down to the habitable zone of the white dwarf. Why would you exclude that possibility? Or maybe there were some claims in the past to find planets post the red giant phase inside where the envelope wouldn't be.
As far as I know, the planetary nebula expand fairly rapidly, and their density becomes fairly rapidly very low. So my understanding is that in a spherical planetary nebula, it's very difficult to reach densities that you can form planets. And the other thing is that the white dwarf will just kind of move away from its planetary nebula on fairly short time scales.
We have planets next to neutron stars, next to pulsars. How is that
Two,
possible?
like two systems.
Yeah, but that's an explosion much more powerful than...
It may happen. So the case where I think it's probably more realistic is in binary stars, because there you can easily form a circumbinary disk from the planetary nebula, from the mass loss. And so you define kind of a plane of symmetry, and you form a circumbinary disk, and you can probably form circumbinary second generation planets. And there are claims that they are detected through transit timing variations, but future will tell if that's correct. So I think that's where you probably can do this fairly easy. And in single planetary nebula, I'm not so sure.
Okay, Charles?
So this follow-up to the first question.
Yeah.
In the solar system, there's a very steady rain of dust inwards from the asteroid belt, just from collisional studies with the Poynting-Robertson track.
Yeah.
And that might suggest an alternative to, a small number of large bodies getting scattered in, which would be more stable, more steady state.
I agree. So when I talk about metal pollution, it's a kind of exponential distribution. You've got a few white dwarfs which have extremely large amounts of metals, and then you've got a tail of many stars that have very low accretion rates. And so in these low accretion rates, I think what you say is exactly the right thing, that you've got dust that kind of constantly gets dragged in. For the ones that have disks around them, we know that there is material very close, and we see in some systems that there's dynamical activity. So in those cases, I would expect, naively, that you have fluctuations in the accretion rate. So in the case of the Nature paper from yesterday, you see that something is breaking up and evaporating, disintegrating, and somewhere you would expect that maybe accretion rate changes. But for that star, we don't have data, so we'll see in a few years if we see metal lines, if they change.
17th magnitude.
Good enough to measure metal lines.
The Doppler tomography work with resolving that disk with the 25-year period is very nice. You mentioned there's some spiral structure in the gas there.
Mm-hmm.
I was wondering if you have a sense of what causes that, and also if this technique could potentially be able to detect gaps due to planets forming in that disk. perhaps not in this system, but in others if you applied it?
So the spiral structure, no, we don't have a very good explanation for that. One thing is that I didn't talk in detail about is the origin of the gas. So about a few % of white dwarfs have dust disks, but gas seems to be not a natural consequence of having dust. And so we must have a mechanism that produces the dust, and we think that it must be collisions. And in that particular case, we think that maybe it's a non-circular disk, and GR will lead to precessions, or different radii precess at different rates, which would lead to collisions, generate the dust. Why that forms a spiral, I don't know. But then most disks have spiral patterns on them. And I think you had a second question, but I forgot that.
Oh yeah, I think I said it wrong. I guess I was wondering.
Oh,
can
gaps.
You see gaps?
Yeah.
Probably not due to planets forming, but just due to any bodies traveling around them.
I think that would be pushing it, yes.
I had very similar thoughts. Ari said it's connected to his question. Usually the canonical wisdom is that there is the planetary nebula and puff it goes. But are there studies that were made, what is the retention of the white dwarf that is left in the middle of the dust? There is a lot of dust in the system. It doesn't mean everything goes out. What amount of it is retained? I haven't seen studies like that made.
Yeah, no, dust may be there, and some of that dust may be brought in through radiation effects onto the white dwarf, but that's possible, yes.
From the original
But-
stellar envelope.
But if that was the case, then you would expect that kind of all stars show that phenomenon, because all white dwarfs we think make planetary nebula. So that should set a base rate of accretion. And it could explain some of the lower accretion rates that we see. So there are several ideas why that may not be a dominant thing. One is the abundances, because the dust of planetary nebula, formed from planetary nebula, would be usually carbon rich, and we don't see carbon in the abundances of the accreted material. The second thing is that in the stars which have a dust disk, we know that there are large amounts of material, so there cannot be dust from the planetary nebula that falls back and forms this, because some of these stars are 500 million years old and they have moved a long way from where they left the planetary nebula. So it may be true for some stars, but I think for the ones that have high accretion rates of carbon poor material, I don't think it will work.
I have two questions, one general, one specific. The general question is, would you expect to detect similar things around other types of star, like main sequence star or neutron star? Similar pollution in terms
Yes,
of
I mean, around main sequence star, there's a lot of discussion in the literature about planets polluting the atmospheres. And I mean, there's the opposite. For the sun, there are people claiming, and that there's controversy about that, there are people claiming that the sun, and I have to see that I get that right, that the sun is refractory poor compared to other solar-like stars because the refractories are in the planets. And other stars would have accreted whatever material there was because they didn't form planets, so therefore they're more refractory. So there's a lot of work going on in main sequence stars.
Because you showed the video that the comet hit the sun, right?
Yeah.
So would you expect the solar spectrum to be affected by that just for a short period of time? And would you expect to detect that?
I don't know. I think a comet in the sun is probably not enough to.
I see.
And the comet doesn't have a composition that is hugely different from the sun. But
Okay. I see. And then I have a specific question regarding the plot which you show the iron to silicon, magnesium to silicon abundance. If you go back to that slide, it seems there is an outlier. Yes. So the pink one,
Yep.
PG1015, this one seems to be quite depleted in terms of silicon, right? And it seems it outlines both the left upper diagram and the lower right diagram.
yep.
So do you have any idea what caused that?
Not in great details. I know that people working on planet formation look at the magnesium to silicon ratio, which can vary by quite a bit and has a strong influence on what kind of planets you can make.
So I have a thought. So when you disrupt an asteroid planet, you are peeling it off from its skin. So initially you may get the composition from its outer layer,
Yeah.
but then as you peel it off more, you start to get the composition of its interior. So if the body that was disrupted is differentiated, then you may be getting like a time sequence view of the body's bulk layer composition, something like that.
Probably,
Yeah.
probably what you see in these the different dots that you see around different stars is like just different parent bodies in their planetary system. So I think I don't know, but that you would that the process would be so gentle that you strip off layers and you can see with time. Yes. So, but what you said is absolutely right. There are some stars that have very large amounts of calcium and aluminium, and so there people claim, it's like the UCLA group, they claim that we see accretion of like kind of crust material.
And then I have one comment, which is the explosion. So I think that makes sense. Maybe the explosion sometimes help to even draw in the material.
Yeah, but they don't explode. White dwarfs don't explode. They're very gentle.
Or this kind of expanding evolution. It may be directional, not symmetric in all directions. So it may be drawing in material from the equatorial plane while pushing stuff out in a polar direction, or something like that. It's just a thought.
Okay.
Thanks.
So one last question at the back, I think.
How far away can you see these spectroscopic lines in white dwarfs?
You mean what distance?
Can you, for example, see them in globular clusters?
No, not yet. So the ones that we study are a few hundred parsec at best at the moment. So if you want to move to 10 kiloparsec, that's a big factor that you need there.
Will at last be able to do it?
Borderline.
Okay, so Boris will be around tomorrow, if anyone would like to make an appointment to talk with him further. And tonight, myself and a few other people are taking Boris out to dinner if anyone else would like to join. But let's say thanks to Boris again.